in this lecture, we are going to continue on with Unit 2, Lecture 4, all about movement. And so in the first part of this lecture, you already wrote down big idea number 14, so you can add right onto that. That was all the types of movement, like extension, flexion, etc. So we are going to add on to those notes. And now we are going to look at levers. And so we talked about joints and the parts of a joint, all those movements that can be formed because joints allow those movements, but joints don't work alone. Joints honestly don't move themselves, they just allow for movement. So we're gonna look at the other parts of this lever system that our bones move upon to allow for all those ranges of motions that you learned about. And our goal, big idea number 15, you can write this down, is to be able to describe a basic lever system and be able to identify the parts of a lever, both on daily objects that you're already familiar with and in the body. So first, we're just going to look at levers in general. What do they consist of? And so a lever itself is just a rigid bar that can move on a fixed point. I would recommend adding these little drawings in. So that's our lever right there, just a flat bar or a bar of some sort that can move on a fixed point. The fulcrum is part of a lever system, and this is the fixed point upon which a lever can move. And so when we draw diagrams of levers, which we will do, we'll label the fulcrum as F. So you can draw this little picture and either color code it like I did, or you can label it as F. Here's like another picture, right? Here's my finger as the fulcrum. Here's my hand as the lever, okay? And it can move upon that point. Effort is the force exerted on the lever arm, causing the bar to rotate, right? So if my hand actually wasn't attached to my arm, this was literally just a bar sitting on this fixed point, the fulcrum, I would need to either push or pull on this bar in some way to get it to tilt. It wouldn't just move on its own, and that's the effort. So I'm going to use an arrow to represent effort, pushing on that bar. And lastly, we have the resistance. So this is the force exerted on the arm of the lever opposite to that of the effort force. So we can get a pointer out. And we use an R to represent the resistance. You'll also see in a lot of diagrams that the resistance is referred to as the load, which sometimes can help make it make more sense, right? So if we look at this block, it's a load on this bar. This block is going to be pulling down the bar this way, whereas the effort over here, whatever that is pushing the bar the opposite way. So they have opposing forces, the resistance and the effort, okay? So these are just the parts of levers in general. And then we will look at in the body, what is the fulcrum, what is the effort, and what is acting as the resistance. Oops, oh goodness. Okay, so also down below, there you can see it now, the operation of most skeletal muscles in our body, so remember skeletal muscles are all those ones attached to bones that move them, involve the use of levers and lever systems. So we have multiple parts of a lever system helping with movement. Okay, so here are, in our body, are the parts of a lever. So in our body, what acts as a levers are bones. Bones are these bars that are going to be moving. What acts as the fulcrum, that fixed point around which these levers can move, these bones can move, is the joints, right? So here's my elbow joint, and it's staying stationary while my bones, the ulnar radius, are moving. The effort is muscles. So if you think about what's allowing my forearm to move up and down, it's my bicep muscle. It's pulling on these bones. So muscles are the effort. And the resistance is the body part that is moving. So in the example I just showed you, the resistance would be the weight of my forearm, of my hand. All those parts are resisting my muscle as it's pulling upward. So the weight basically of the body part that is moving. If I was standing on my tiptoes, my whole body would be the resistance. All that body weight is being moved. And that's big idea 15. So with big idea number 16, now we're going to look at the different types of levers that you'll find in life and in the body. And each has a different purpose that it serves. Once we can differentiate between these levers, and a way in which we can do so is by calculating the mechanical advantage for each lever system provided. So we'll look at what mechanical advantage is in here and a little equation for that as well. So starting off with mechanical advantage, when we're looking at a lever system, we want to calculate, does it have a mechanical advantage? And what mechanical advantage is the ability to do work with less effort. Sounds pretty nice, right? Like you could do all your homework with less effort, mechanical advantage, if you had the right tools. So mechanical advantage we can find by using this formula. It's the distance from E to F over the distance from R to F, or divided by. So sometimes people forget that it's the distance between, right? So if we have E and we have F, we have to find like what's in the middle. We have to subtract them, and we use that positive number. So effort to fulcrum over the distance from resistance to fulcrum. EF over RF. I always think like fulcrum's in both, but ER, right? E's on the top, R's on the bottom. So that helps me remember which one goes where for memorizing this formula. You could also write it as this over here. However, you just have to be careful, right, that you remember it's the distance between. So either way. So just kind of like a cheat sheet is almost saying that there is a mechanical advantage when the distance from E to F is greater than the distance from R to F. When the distance from the effort to the fulcrum is greater than the distance from the resistance to the fulcrum. In other words, when the mechanical advantage, when you plug in that equation, it ends up being a positive, or a number greater than 1. Sorry, not a positive number, but a number greater than 1. So let's take a look at that. So if the mechanical advantage is greater than 1, there's a good advantage, meaning there's less effort needed to move the resistance. Right? And the resistance is, again, the weight of that body part that's being moved. So there would be less effort needed to move that, which is a good thing, a good advantage. Now, if the mechanical advantage ends up calculating less than 1, like 0.25 or 0.75, then there's a poor advantage, meaning that it can still move this part, there's just going to be more effort needed to move that resistance. And so when we look at some scenarios in real life, we kind of see how this plays in, certain tools you use, like a shovel versus a wheelbarrow versus scissors versus a stapler, and how much effort is needed for each. So here's our first type of lever. I would recommend drawing this out, labeling it just as it is in your notes. So with first class levers, we identify them by the fact that the fulcrum is in between the effort and the resistance. It doesn't have to be smack dab in the middle, it just has to be somewhere in between them. So the fulcrum has to be in the middle, first class levers. So each lever class has a different type of mechanical advantage. So we're going to try and figure out for first class levers, do these have a mechanical advantage? Do they not have a mechanical advantage? Do they sometimes have a mechanical advantage? What is the deal? So here's our first practice at using that formula. Mechanical advantage is the distance from E to F over the distance from R to F. So we'll do this one together and I'll have you do the rest on your own. But does this lever give a favorable mechanical advantage? When we plug in that formula, is it greater than 1? So what you want to do is the distance from E to F is 4. And we want to divide that by the distance from R to F, which is 1. So the mechanical advantage is 4, which is definitely greater than 1. So it does have a favorable mechanical advantage. You can move something with less effort. Now, we could also have a system set up like this. Notice the fulcrum is still in the middle, so it's still a first class lever. But now, if you calculate the mechanical advantage, I want you to type in the box, what number did you get? Hopefully, you got 0.25 or 1/4, which does not give a favorable mechanical advantage. So you can see both of these are first class levers. Therefore, if we're looking at a lever, and it has a mechanical advantage, or maybe it doesn't, we still wouldn't, it could still be a first class lever. In other words, first class levers could have a mechanical advantage, or maybe they don't. It could go either way. So you definitely want to write that down. First class levers can be less than 1 or greater than 1 in terms of their mechanical advantage. Okay, so let's look at some first class levers in life, right? So here's a bunch of pictures that can help you start to visualize this. Get my little pointer out. So first we have pliers. Again, first class levers are identified by the fact that the fulcrum is in the middle. So notice here's the fulcrum in the middle. This is what everything's moving around. This little nail or whatever it's called doesn't move, but on this side of the nail, things are moving. On this side of the nail, things are moving. So we have the effort applied here. This is where someone's hands are going to grab those pliers and squeeze. And what's resisting the person's movement or their effort is the load. Whatever goes in between the pliers here, the load or the resistance goes right on here. So fulcrum's in the middle. Another example is scissors. Again, notice the fulcrum is in the middle. They work similarly to pliers. We apply effort over here. They move around this fixed point. And the resistance or the load is whatever we're cutting, paper, fabric, whatever that might be. Here we have someone rowing a boat, okay? So when oars are used for moving water, if you look, we have the person is the effort, they're pulling on the oar. The water is resisting this person's movement, and the fulcrum is basically right in the center of the oar, the part that's kind of moving back and forth right along the boat, or not moving, it's actually sitting there, but allowing the other parts to move around it. Down below on the left, we have this woman using a crowbar. The fulcrum is right here. Right here doesn't really move on the crowbar, just everything around it moves. She's applying an effort and she's able to move this giant load here because if we look, the distance from the effort to the fulcrum is greater than the fulcrum to the load. So it makes it easy to move this giant rock. And lastly, another example is a hammer when pulling out a nail with the claw. So the fulcrum is the head of the hammer right here. This is where everything's moving around. The person's effort is up here, and the resistance is the nail itself. So again, the fulcrum is in the middle. That's how we know it's a first class lever. So let's look at 2 examples in the body. We have, number 1, extending the arm using the triceps. Notice how specific this is. So this is our movement, extension, and using the triceps. So here's your tricep, and I'm trying to go like this, right? So we'll talk all about muscles in the muscular system, but muscles can only pull. They can't push. So we're not using the bicep to extend our arm. Biceps pull. They can do flexion, but extension is the tricep. This muscle is pulling. It's squeezing to lower our arm. So if you look at this muscle, here it is, and this muscle connects all the way up from our scapula area and the top of the humerus all the way down to the olecranon process. Now, the fulcrum is in the middle. Look at the fulcrum. It's the joint between the ulna and the radius and the humerus. That joint is right here. So we have our effort, our fulcrum in the middle, and then the resistance or the load is the forearm. That's a first class lever in the body. Again, you can kind of see like right where, here's the humerus, this is flipped around, the other arm, and you can see that the muscle connects right here to the olecranon process, but the fulcrum, the joint, is right here, more in the middle. Next, we have tilting the head backwards like this, right? So here, the fulcrum would be like this, the foramen magnum over the atlas and axis of the vertebrae. We have that in the middle. The effort would be your neck muscles pulling backwards, and the load or the resistance is all of your face muscles, specifically your mandible, which is really heavy, resisting that effort. So this should all be something you already have down, but just in review, we have F in the middle for first class levers. Sometimes they have a mechanical advantage and sometimes they don't. Some examples are tilting the head back, extending the arm using the triceps, sorry about the numbering, pliers, scissors, oars for when used to move water, and a crowbar. So those are all examples of first class levers. Next, we have second class levers. So instead of the fulcrum being in the middle, now the resistance is in the middle. This is the key characteristic we can use to identify second class levers. So what type of mechanical advantage do second class levers have? Do they have a favorable one or an unfavorable one? So you want to use your equation and calculate this. The distance from E to F over the distance from R to F. Hopefully you found that the mechanical advantage is 5. So it's greater than 1. So second class levers do have a favorable mechanical advantage. They're going to be able to move something with very little effort. So let's look at some examples in life. Again, the resistance is in the middle and they're always going to have a favorable mechanical advantage. So a paper cutter, check this out. Those are so easy to use, right? You barely have to even put any force. You can cut right through a whole stack of paper. Here we have our fulcrum right here. The effort is way over here on the handle, and the resistance is in the middle. As you're cutting the paper, it's resisting your effort to push down on the paper cutter. Wheelbarrow is another one. Think about how much heavy stuff you can lift in a wheelbarrow with such ease. And so with a wheelbarrow, we have the fulcrum as the wheel in the front. The effort is you lifting up on the back of the wheelbarrow, and the load or the resistance is everything in the bucket in the center. So R is in the middle, resistance, or also sometimes called load. In the body, here's one example of a second class lever. Standing on your tiptoes. So we have this calf muscle working with your Achilles tendon to pull your body or your upward, right? Your heel upward against gravity and against the force of your whole body that's resisting this motion. So the load or the resistance is in the middle, your entire body weight coming down through your tibia and fibula onto your foot muscles. The fulcrum is here in your metacarpals. Okay, in your phalanges, that joint right there. So just to review, R is in the middle for second class levers, that resistance, or sometimes it's called the load. There's always a mechanical advantage, and you do have to add this in right here. Second class levers are often called power levers. They can lift really heavy loads because they have such a great mechanical advantage. They can lift really heavy loads. Think about the whole load of your body weight. Think about the load you can carry in a wheelbarrow. And so those are some examples that we already talked about. Okay, lastly, we have third class levers. So this is where effort is in the middle. So FR, and now we're at effort. So go ahead and do the math. Do third class levers, if this is an example of one, have a mechanical advantage? So the distance from E to F over the distance from R to F. Hopefully you found the mechanical advantage is 1/5. So it does not have a mechanical advantage. It's less than 1. So make sure you write that down. Poor mechanical advantage. It's something that's going to always be less than 1. Only first class levers can go either way. But with third class levers and second, that's not the case. Third class levers always have a mechanical disadvantage. So let's look at some third class levers in life. Tweezers, if you're tweezing your eyebrows or whatever you're tweezing, those are a third class lever. Sweeping with a broom, salad tongs, and shoveling. So with tweezers, the effort is in the middle, right? You squeeze the tweezer in the middle and the load is whatever you're tweezing. At the edge, fulcrum right here. This is that fixed point. Everything's moving around. With a broom, it's a little bit harder to see, but you would hold the broom at the top, right? So that's your fulcrum. Your effort is your sweeping hand, the one that's moving like back and forth. And the resistance is whatever you're sweeping. Here again, kind of set up like tweezers, we have salad tongs. Your effort goes right in the middle, fulcrum's over here, and resistance is whatever you're picking up. So effort is in the middle, third class lever. And lastly, shoveling, right? You have one hand over here, and that is the fulcrum. You have this one that's moving up and down. That is the effort, and the load is whatever you're shoveling. If any of you have ever shoveled snow or had to shovel anything that's pretty heavy, it's pretty tough, right? So it's not nearly as easy as like moving a wheelbarrow. So third class levers in the body. Here's an example. The bicep flexing the arm, okay? So here we have to look at where the muscle attaches to the bone. That's what really is what we're focusing on. So we have to first find each part. We have the fulcrum right here, the joint of the elbow. We have the effort, which is the bicep muscle pulling the arm upward. So effort is right here. And then we have the resistance. Maybe you're holding a weight or maybe you're not. Your forearm is still enough resistance, going kind of gravity's pulling it in the opposite direction. So again, notice that the effort is in the middle here. And that's how we know this is a third class lever. It's where that muscle specifically attaches. You'd have to see a picture at this point in our knowledge to know what kind of class. Where does that muscle attach? So in review, for a third class lever, E is in the middle. This you have to add on in. So we already talked about how they always have a mechanical disadvantage, but they're called speed levers. So while it still takes a lot of effort to move these portions, since they have that mechanical disadvantage, they are speedy. So there's a different kind of advantage, not mechanical, but they do have a speed advantage. So they can move a load rapidly through a long distance, but require more effort. So mechanical disadvantage, but speed-wise, they're actually advantageous. And so most muscles in the human body are third-class levers. While force is lost, speed is gained. So over time, through time, we have needed that ability of speed to stay alive. And so that, in the older times. And so that has allowed our body to kind of evolve into having mostly third class levers. We went through these examples already: flexing the lower arm, tweezers, sweeping with a broom, salad tongs, and shoveling. Now there are other examples in the body, but we'll look at those as we do practice worksheets and so on. So just have at least this one down. Okay, to summarize, or just kind of not even to summarize, but a little trick to help you remember, as you're identifying lever classes, you can either look at and kind of discover and do math to figure out, is there a mechanical advantage or not? And that can kind of help you differentiate between second and third class. But the easiest thing to do is to remember this trick: FRE 1, 2, 3. F comes first. F is a first class lever. R comes second. R is a second class lever, and E is third. E is a third class lever. Or when I say E is a third class lever, I mean these are the ones that are in the middle. So in a first class lever, the fulcrum is in the middle, F. In a second class lever, the resistance is in the middle, R. And in a third class lever, the effort is in the middle, E. So FRE 1, 2, 3. We're talking about what's in the middle. How can we determine what type of lever class we're looking at? Okay, so that's it. We will practice this. We'll do a pair deck tomorrow. We'll talk about it more. There's a worksheet coming up, and there's even a lab to help you practice with mechanical advantage. So we will practice this quite a bit. So hopefully you have a good basis down in your notes, and that is the end.